And we are back. All right, we're going to skip ahead to chapter 19, and we are going to talk about these first two sections in chapter 19, 19.1, and then tomorrow in class, we're going to go over some of 19.2, which has to do with the half-lives of radioactive decay. So this first section has to do with the different types of radioactive decay. And first off, we are going to review what we already introduced 2 classes ago, the nuclear notation, in which we can help differentiate between the different isotopes of different atoms, where X is the chemical symbol, and then A at the top left as the superscript is the mass number, the sum of protons and neutrons. The bottom number Z is just the number of protons. So there are actually 3 different isotopes of carbon. So the 3 different ways they would be represented is there's carbon 12, carbon 13, and carbon 14. And what's different about them, obviously here the mass numbers, but what's different about them, what causes a different mass number is the different number of neutrons. And you can get the number of neutrons simply by subtracting Z, the atomic number, from the mass number A. So always, if you take the mass number, the number of protons plus neutrons, subtract by Z, the atomic number, the number of protons, as a result, you get the number of neutrons. So that means the carbon on the left has 6 neutrons, carbon in the middle has 7, carbon on the right has 8. And remember, for each of these, you don't necessarily have to have the atomic number, because as soon as you see the letter C, that means carbon, and you can look on your periodic table and see that that element has the atomic number 6, so 6 protons. Also remember, if these are ions, that means the number of protons and electrons is not equal, and you should input the charge, indicate the charge at the top right, as a superscript. And remember, with the charge, you always put the number first. So if it's +2, you should put 2+. Okay, so this nuclear notation is important when we are writing out the different types of nuclear decay. And with nuclear decay, it's a little different than chemical reactions. So chemical reactions, what's happening, remember, every reaction obeys the law of conservation of mass. So with chemical reactions, it's just the rearrangement of atoms. Whatever atoms are present at the beginning of the reaction are present at the end. It's just they're in a different formation, a different rearrangement. So radioactive decay is a little different because you start and end with different atoms. So nuclear reactions are different because you're producing new atoms. And some elements are more likely to undergo nuclear decay. So the ones that are more likely to go under nuclear decay are those that have an atomic number greater than 82. So atomic number greater than 82. And also in general, if elements have even numbers of protons and neutrons, so even numbers of protons and neutrons, that means they are likely to be more stable. Okay, so atomic numbers greater than 82, atoms are more likely to undergo radioactive decay, but then if they have even numbers of protons and neutrons, they are more likely to be stable. So still always in these different types of radioactive decay, still mass is conserved. And you will see for the lighter elements, which are down here, there's usually the neutrons don't necessarily have to equal the number of protons, but with the lighter elements, it's generally the case where the number of neutrons is close to the number of protons. Whereas a lot of the heavier elements, if you look at the line here, that is not the case. In general, there are more neutrons relative to protons. So you should just realize that the lighter elements, neutrons and protons, are about equal, but then once it gets to the heavier elements, there gets to be more and more neutrons in order for there to be a stable nucleus. Okay, so the first type of radioactive decay is alpha decay. And we've already talked about alpha particles with Rutherford's experiment. So how we represent an alpha particle, or alpha decay, is the Greek letter alpha, which writing it out, it looks like a little fishy, like that. Or an alpha particle is a helium nucleus. So we write out helium. It has a mass number of 4 and an atomic number of 2. And remember, we already talked about this with Rutherford's experiment. The alpha particle is positively charged. Okay, so with alpha production, or sometimes it's called alpha decay, always what happens is an alpha particle is produced. An alpha particle is on the product side of the equation. So let's say, we'll have another example here. But let's say I say thorium-230 undergoes alpha decay. Okay. So automatically, since I put the symbol TH, and you should have your periodic table out, so you should be able to find thorium TH on your periodic table. It has an atomic number 90. And let's say I say, okay, thorium goes under alpha decay. So automatically, one of your products, you should put an alpha particle, the 42He, and then you have to figure out, okay, what is going to be the other product here? And still, the law of conservation of mass applies. So the mass number is going to stay the same, and the atomic number is going to stay the same. So on the left side of the arrow, we have a mass number of 230. So that means overall on the right side, we need a mass number of 230. So that means altogether, 4, you have to think about 4 plus what equals 230. So that has to be 226. And then for the atomic number, we have an atomic number of 90 on the left side. So on the right side, we want the overall atomic number to add up to 90. So 2 plus what equals 90. So that has to be 88. And then you find 88 on your periodic table. That atomic number represents radium, of which its symbol is Ra. Okay, so for alpha decay, from the original particle, from the thing that's from the species that is undergoing decay, the mass number of the new particle decreases by 4. And the atomic number decreases by 2. Okay. And in general, of these different types of decay, alpha decay is the least dangerous because it is the largest of the 3 types of decay, the alpha particle versus the other 2, and it is also charged. So in alpha decay, it can be blocked by just a single piece of paper. So it is quite easy to block in comparison to the others. So the next one is beta decay. So it is either represented by the Greek letter beta, which looks like a cursive B, or a beta particle is essentially just an electron. So we write it out in terms of its nuclear notation as E. And then since the electron has such a small mass, we assume its mass number is 0. And then, since it has a charge of -1, it doesn't have any protons in it, so it has no atomic number. So since its charge is -1, we put its atomic number as -1. Okay, so with beta decay, always the beta particle is one of the products. So another example here, let's say I say iodine, the mass number of 131 is undergoing beta decay. So first off, you already know iodine, you find it on your periodic table. It has in group 17, it has a atomic number of 53. And if I say, okay, this undergoes beta decay, that means automatically you know the beta particle, or electron, has to be a product. And then we have to figure out, all right, what's left over here, knowing that both the mass number and atomic number are conserved. So first off, we start with a mass number of 131. For this part, it's easy. The mass number of the electron is 0, so it remains, the mass number here remains 131. But the tricky part here is we start with an atomic number of 53 and on the left side. Now on the right side, -1, you have to think about -1 plus what equals 53. And the answer is not 52. Don't treat this -1 as a positive one. So -1 plus 54 equals 53. Okay, and now you find 54 in your periodic table. That is xenon with the symbol Xe. So that is our correct product. So with beta decay, so the mass number remains the same, RTS, but the atomic number now increases by 1. So the atomic number increases by 1. Okay, so what we're essentially doing in beta production, we're essentially changing a neutron. You're changing a neutron to a proton. Okay, and since an electron is much smaller than a alpha particle, than a helium nucleus, however, it is still charged, it can be blocked by aluminum foil. So if you try to block it with paper, it will go through, but something stronger, like aluminum foil, it will be blocked by that. Okay, then the final one is gamma decay. So a gamma particle is represented by the Greek letter gamma, which looks like an up and down fishy. And gamma is the most dangerous because it has no mass, so its mass number is 0, and it has no charge, so its atomic number is also 0. And normally, it accompanies other nuclear decays. So like this, this one right here, we have 2 gamma particles that are produced, but they're produced in conjunction, or along with, alpha decay. And essentially what a gamma particle is just excess energy. And so it's the most dangerous since it has all that excess energy. It releases so much excess energy. And since it has no mass, it has no charge, it is only blocked by either lead or concrete. Okay, so those are the 3 different types of nuclear decay. Alpha decay, which is just a helium nucleus, and it's represented by 4,2He. Beta decay, where a beta particle, an electron, 0-1e is one of your products. And then gamma decay, which is the most dangerous since it releases so much excess energy and can only be blocked by lead or concrete. All right, that's all for today. See you next time.